Alright.
My dad just shut it off because he didn't want to.
Covalent bonding. So recall in ionic bonding, the electrons are completely given up. In covalent bonding, the electrons will be shared. So a little review. Recall that bonds are the attractive force between atoms or ions in a compound, and they depend on the electron configuration. This part isn't going to be on it yet, on the little handout I gave you. It depends on the electron configuration, specifically the valence electrons, and the electronegativity. Why do elements bond? They bond to achieve a stable electron configuration, which is 8 electrons, except for hydrogen and helium, which only need 2. This is the octet rule. Atoms will lose, gain, or share electrons to achieve a stable configuration, which is 8, except for hydrogen and helium, which is 2. In other words, they're trying to get into the lowest possible energy state. Everything wants to be in the lowest possible energy state. So, ionic properties, let's review those too. They exhibit a crystal structure, typically at least, exist as a solid, dissolve easily in water, have high melting and boiling points, conduct electricity in solutions, and have high electronegativity differences. And again, these are typical properties, not all the properties for every single element or compound. So this is where the notes begin. Covalent compound properties. They usually have low melting and boiling points. They do not dissolve easily in water, and they do not conduct electricity in solutions, and they can exist as gases, liquids, or solids, and have low electronegativity differences. So, like for example, sugar is a covalent compound. Sugar, though, does dissolve easily in water, so it doesn't typically behave like normal covalents. It does have low melting point. You can melt sugar. Salt is ionic. Salt, even if you took a lighter to it, it will not melt. It needs a blowtorch to get it to melt. And but even compared to salt, sugar does not dissolve as much as salt does in water. So, some common covalents. Nitrous oxide, that name's actually wrong, but this is the common name of it. We usually don't go full proper name on the common things. Mostly we call it laughing gas. Methane, which is your natural gas in your homes, it's CH4. Sugars is actually a family. There's sucrose, there's glucose, there's fructose. There's lots of different sugars. Table sugar is sucrose, I believe, while blood sugar, what your body converts it into, is glucose. Then hydrogen peroxide, carbon dioxide, and water are one of the 2 most famous examples of covalent. CO2, carbon dioxide, has many uses. Water is a very typical example of a covalent. So a covalent bond occurs when valence electrons are shared between atoms, usually between non-metallic elements. Covalently bonded a compound known as a molecule. These shared electrons are part of the valence of all atoms involved and to satisfy the octet rule. Since electrons are shared, no charges appear. Many combinations can occur between 2 nonmetals. Carbon and oxygen can form either carbon monoxide or carbon dioxide. So if I ask you what does carbon and oxygen make, well, it can make multiple different covalent compounds. And unlike with ionic one, where there's a single formula unit for covalent, you just by knowing which elements are involved, you don't know the formula. That's because it usually takes a significant amount of energy to get them to react. For example, the pencil lead you're using to write with, if you're using a pencil, or diamond is made of pure carbon. Air is about 20% oxygen, and they don't react. Your pencil lead isn't reacting to make carbon dioxide or carbon monoxide. It takes a little bit of energy into it. However, if you heat it up, it will start burning and start making carbon dioxide. And that's the end of the day one PowerPoint. What I did with the other class is start on Lewis dot. We did it for single elements. What about compounds? Remember, that was the bonus question.
Okay. So that's typing.
So, this was the bonus question on a previous test, CO2. So, we have carbon with its 4 electrons. We have oxygen with its 6 valence electrons. And we have another oxygen. And I'll go more later when we get to it in depth about how you set this up. Now I want to see if y'all can figure out some things. So here we can see that, again, every element wants 8 electrons, except for hydrogen and helium. This has 6, that has 4, that has 6. They need to come over and do some bonding. So if we look, there's a missing spot here, and there's a missing spot here. There's a missing spot here, and there's a missing spot here. We can take this electron and share it with this carbon. We can take this electron and share it right here and have these two shared. And likewise, we can put this one and share it over here and this one share it over here. And get have them share it between them. So, 2 ways to draw this. So I'm going to come over here and do that. Take and move these over here. And likewise, these are going to be shared on the right side. And oxygen is going to share its 2 electrons. So I'm putting it like that, and then we have 2 over here. So this oxygen is going to share 2 of its electrons with the other one, and it has 4 that are not being shared. So if we count all the electrons next to each atom, this has 1, 2, 3, 4, 5, 6, 7, 8. This one has 1, 2, 3, 4, 5, 6, 7, 8. And this one has 8 also. Another thing is if we have 2 dots being shared, we replace it with a single line. So you can either write it off to the side, as long as they're paired up. You can replace those with a single line. Usually I don't like slanting them. What I would prefer is something like this. This would be the correct Lewis dot for CO2. So oxygen is sharing 2 of its electrons with carbon. Carbon is sharing 2 of its electrons back with this oxygen, and it's symmetric on the other side too. So carbon is sharing 2 of its electrons, it has 4, so it's sharing half of its electrons with this oxygen, another half of the other, and each oxygen is sharing 2 of the electrons with the carbon. Make sense? Let's look at, I want you to attempt this. Carbon monoxide. What would be the Lewis dot structure for it? By the way, we call a single line a bond. So if we have 2 of them, this will be called a double bond. If we have 1 line, it's called a single bond. And if we have 3 lines next to each other, it's a triple bond. I don't think I've seen anything higher than a triple bond. What'd you get, chat? You get.
That's just a little. No.
Cricket, I guess so. What do you have, Chloe?
Yeah, she was just the same thing.
Yeah.
Okay, is it just basic? Should it not be one on the bottom, one on top, 3, 2, 6?
Count how many dots are around it, each atom. It doesn't complete the octet rule.
No. If you add 2 more.
Alright, so we got carbon. Carbon has 4 electrons. And we got oxygen.
Would oxygen need to share 2 more with carbon to make it full?
So we have an easy thing we can look at immediately. The very easy thing is noticing that these single electrons on the side, so this one's missing. And this pen dried out over the break. Want something light? So, let's see if this dried out. So first thing you notice is this is missing a spot, this is missing a spot, so these two electrons can pair off and form a bond. Likewise, this is missing a spot right here, this is missing a spot, these can form a bond. So I can go ahead and do this. And one thing you should note is on a molecule, you will never have an electron by itself. So I'm going to go take these two remaining ones and go ahead and pair them off, make an electron pair. And then I'm going to have two electrons here that are going to be shared along with two oxygen electrons, like this. And I'm going to go ahead and replace these with lines. Actually I won't. Not yet. So looking at this, how many electrons are on the oxygen? 1, 2, 3, 4, 5, 6, 7, 8. Yes, carbon has shared two of its electrons with it. And how many is on the carbon? So, how are we going to remedy this? So, let me redraw it. What do you think is going to happen? So, carbon needs two electrons, so what do you think is going to happen? The oxygen is going to share two of its electrons.
Oh, okay.
So these two electrons right here, oxygen is going to share it with the carbon. 1, 2, 3, 4, 5, 6, 7, 8. And then 1, 2, 3, 4, 5, 6, 7, 8. So we have carbon with a triple bond with oxygen. Again, each line represents two electrons. I will say this. In this notation, it kind of hides the fact who's sharing the electrons with who. But it really doesn't matter because all we really care about is how many bonds are between it. If you can see with colors that oxygen is sharing 1, 2, 3, 4, 4 electrons with carbon, and carbon is only sharing 2 of its electrons with oxygen. So if you were to count it like this, each line corresponds to 2. So there's 3 lines, so that's 6 plus 2 is 8. 6 plus 2 is 8. Each one has. So let's do a very difficult one now. Go let y'all attempt it for about 2 minutes, and then I'm going to give you a hint. Let's do laughing gas. Dinitrogen monoxide. I think I should go ahead and give y'all a hint. Y'all should have already started, right? Y'all started, right? How many of y'all started like this? N-N-O. I will give you a hint. This is the correct way to start this. Do not put oxygen in the middle.
Of course it is.
I would have too, but there's some rules. We'll go over the official rules later. But you put whatever has the least electronegativity in the middle. Except for hydrogen. Hydrogen always goes on the outside. So nitrogen has less electronegativity than oxygen, so it should be the middle one. I didn't tell the other class about it, and then I had to correct it after he spent working because I couldn't figure it out. If you put oxygen in the middle, there's no possible way of doing it. This is actually, even though this is difficult, there are 3 possible answers.
3 or 30?
3.
Oh, I thought one of us got to get it.
Out of 3 possible answers, only one's like truly correct, I think. They're called resonant ones. They bounce between the different states.
And B,
I definitely do not. Nope.
I just did the dots. I didn't do the line. No.
You have way too many electrons around one of them. I think your central atom has 10. Close though.
Oh, okay.
You forgot to give the nitrogen electrons to the other side when you drew it. So nitrogen has how many valence? 5.
Oh no, I was looking at that's where I messed up.
Nitrogen has again 5.
I was looking at it as a common number. Not number. Yeah.
Oxygen has 6. So, multiple ways we can approach this. Again, I see a spot missing right here and a spot missing right here. I can connect these with a bond. Yes. And I'm going to take this right here and this right here. It's a missing spot here. Connect that with a bond. Missing spot here. Missing spot here. I can connect these two with a bond. So what I end up with is oxygen is going to share 2 of its electrons, which means these 2 will be left on the side. While nitrogen shares 2 of its electrons back. So let's see if oxygen is satisfied. 1, 2, 3, 4, 5, 6, 7, 8. All right. And I'm going to share 1 of these with the nitrogen. And I'm left with, and we have 2 pairs right here. I'm going to group them up like that. So I moved this one up to the top right here. And let's count and see what we have. So we have 8 on this one. We have 1, 2, 3, 4, 5, 6, 7, 8 on the middle one. And 1, 2, 3, 4, 5, 6, 6 on this one. So, like last time, we're going to make the middle nitrogen share 2 of its electrons to get the left one up to 8. Double check. 1, 2, 3, 4, 5, 6, 7, 8. This nitrogen is good. 1, 2, this 4, 4. That right there is 8. And right here, 1, 2, 3, 4, 5, 6, 7, 8. Everything's satisfied. This is a possible solution. Alright. So let's do this again. Now I know one of the most stable configurations is a triple bonded nitrogen atom. So what I'm going to do is go ahead and do the triple bond and see if I can work from there. So these two are going to match up. These two are going to match up. And these two are going to pair off. So I'm left with bond right here. These 3 on this side. These 3 over here. These 2 on top. And then I'm left with oxygen over here by itself. Can I add oxygen to this? Well, here's one thing we need to look at. How many are already around here? We have 8. How many are on this nitrogen? 8. And oxygen has 6. So this tells us that oxygen isn't going to share any of its electrons. Instead, nitrogen is going to just share 2 of its with the oxygen. So what we end up with is something like this, where oxygen is going to keep all of its electrons to itself. Double check the count. 1, 2, 3, 4, 5, 6, 7, 8. This nitrogen has 8. 6 plus 2 is 8. And 6 plus a 2 from the nitrogen is 8. Octet rule satisfied. So nitrogen triple bonded with a nitrogen, the single bond to oxygen. This is also a possible solution. I'm just going to go ahead and write the answer to the last one as it's hard to explain, or at least doing how I've been teaching. So we have 2 electrons here, 2 electrons here, 1 here. And here's a little ionic bonding, where the middle nitrogen gives up. This is the only example I can think of where this happens. This is actually unstable anyway. It is a possible solution, but it's the most unstable. So nitrogen, single bond with nitrogen, a triple bond with oxygen. This is a possible solution. These are known as resonating structures. The electron doesn't, the electron being shared isn't fixed. We can see that in this situation, this is actually the most stable one. Usually it doesn't change from this, but if something happens, an electron, let's say one of these electrons moves over to oxygen and we get here, then the electrons can be shared differently. So here the electrons are mostly being shared between nitrogen and nitrogen, where 2 electrons from the nitrogen is being given to the oxygen. But whenever they're being shared back, sometimes the electrons can go over here and be shared like this. Sometimes the oxygen will share too many and come over here during it. And what happens is it cycles back between all of these. It's never in one single configuration. It's constantly changing. This one is the most stable. This is stable, and this is very unstable. We'll look later on in more detail. But are y'all starting to figure it out?
Yeah.
Besides this one, I don't recommend ever trying to do any ionic bonding at the same time. Where, yeah, this solution, it just ends up. There's a shortcut to doing this that makes it work.
I think it's only not stable to then bring it off the phone.
Alright, try this one. This one. And this one. These 2 are super easy. For the first one, let me recheck. Is that a positive or is it a negative? It is a negative. So the first one is an ion. There's a charge of -1. Y'all figure it out. So these are easy too. We only got like a minute or two. Oh, wait. I still get confused. Never mind. Yeah, I was thinking 1027. So these two are very easy. So carbon has 4. So it needs 4, but luckily we have 4 hydrogens. So hydrogens can come fill these gaps. And hydrogen only needs 2 electrons. So 1, 2 for the hydrogen, while the carbon in the middle has 8. So this structure looks like this. Likewise, the same thing for water. We can come over here and fill these spots with hydrogen. Hydrogen now has 2, so it's happy. That's the exception to the octet rule. Hydrogen and helium only need 2 because they only have 1 energy level. Oxygen now has 8, so that satisfies the rule. this one's an ion. So let's ignore the ion bit for now. Just what does it mean to have a charge of -1? I've done what? Gained 1 electron. So keep in mind that we're going to add 1 electron in later. So let's start with nitrogen has 5. Oxygen has 6. Let's go ahead and group up these two and these two. Move these two to the left, and I'm moving these two to the right. And let's count. 1, 2, 3, 4, 5, 6, 7. And over here we have 8. This one is missing 1 electron, but this needs 1 electron to make it negative. So let's go ahead and add that electron right here. So this is, or 1 electron I added to make this negative. And now this satisfies the octet rule. And put brackets around it to indicate that it has a charge. So double bond. It looks like that. Makes sense? Does it make sense? Not getting it?
So I wrote H and then I wrote my line and then I put 2 electrons above and 2 below.
So for water?
Yeah, does it matter if the structure matters?
Yes. So that's actually what I was about to do a preview of. So how well do you have to get this down? So looking at future. So here's what it looks like when we have a central atom with 2 molecules attached to it. If I add 2 electron pairs here, and then let's hide the lone pair. This is what water will look like. It has a shape that is bent because these electron pairs are trying to get as far away from each other as possible. And these are trying to get away from each other as much as possible. And because we can't really see electron pairs whenever you hide them, it gives you a structure that is bent. And if you show the angle, this is 109.5 degrees. Let's see if I can't add. So something that looks like this versus something that looks like that. So we have to know what the shape of the atoms look like.
Excuse me, teachers and students, at this time, if you would go ahead and release the varsity girls basketball team and managers to meet Coach Bowles down in the gym. Varsity girls basketball team and managers need to be released at this time to meet Coach Bowles down in the gym.
So, you need to be able to look at a formula and tell me what shape it's going to be in. In order to do that, you need to write the Lewis dot structure, figure out how many lone pairs you have, and then luckily it's nice and neat. You don't have to imagine the forces involved. If you have 4 electron pairs, 3 of them bonded, and 1 of them a lone pair, it makes this. Which you can kind of visualize or think in your head how that would look like. So let me add this. So if we have this, if I replace an electron pair with just another one here, it makes the exact same structure. The only difference is I think the shape is the exact same overall. It's just that when you hide the electron pair, what left is the overall shape of the molecule. It's called the molecular geometry versus the total geometry, which is known as electron geometry. But that's what we're going to be getting into.